This is the video for our final E&M project, and here we are exploring the relationship between the Maxwell laws and the electromagnetic wave functions. And this is Yichen.
This is Ray.
We are familiar with four of Maxwell's equations. If we wish to see the equations written in differential form, we have to apply the fundamental theorem of calculus. As an example, we will use Ampere's law. The fundamental theorem of calculus allows us to rewrite the integral form as a curl form, and thus allow us to simplify the area from both sides. This gives us the differential form. If we apply a similar process to all the rest of Maxwell's equations, we get the differential form of all four of Maxwell's equations. If we consider the equations in a vacuum, the charge density and current density are zero. Thus, we can further simplify Ampere's law. Now that we have Maxwell's equations written in differential form, we can find the wave equation by taking the curl of Faraday's and Ampere's law. By applying the vector triple product expansion, we are able to take the curl of a curl, and by further simplifying the equations by applying Maxwell's equation of del of E equal to 0. We can further simplify the equation by simplifying the general case in the z direction, thus simplifying the del squared to d squared over dz squared. If we apply a similar process to Ampere's law, we are able to get the magnetic field's wave equation. Both wave equations state that a change in the electric and magnetic field in space will result in a change of the electric and magnetic field in time.
A plane wave is a form of wave whose waveforms are parallel planes. In the case of electromagnetic waves, the E&M field oscillates in the plane and the plane is perpendicular to the direction of propagation. So here we have the solution to the wave equations as the form of electrical and magnetic field. And we're going to show that the equation satisfies the wave equation and as well as Maxwell laws. The solution to the wave equations will result in a plane wave in the Cartesian coordinates. The wave equations can also be solved in other coordinates like the spherical coordinates, but these will not be discussed in this video. E0 and B0 here are the amplitude of the electric and magnetic field. The K here is the wave number and omega is the angular frequency. By plugging the solution into the wave equation, we can get the relationship between omega and K, and we get that omega equals K times c, where c is the speed of light, which is also the speed where the wave is propagating in the z-axis. We also know that our solution to the wave equations needs to satisfy the Maxwell's laws. Here, we'll take the electric field as an example. We know that from the Maxwell's laws, the divergence of E field equals 0, and the curl of E field equals the time derivative of B. So after we plug in our solution to these equations, we can get that E0 dot K equals 0, and E0 cross product K equals omega times B0. And here, the K is a vector pointing in the direction of propagation, and so we know that the E field, the B field, and the direction of propagation is mutually perpendicular to each other. And we can also get that B0 equals 1 over c times E0, which gives us the relationship between the magnitude of the magnetic and electric field. The results show that our solution to the wave equations is a plane wave. By doing this project, we have successfully derived and confirmed the wave equation with the differential form of the Maxwell's laws. And we also learned about some key features of a plane wave and how they are being derived from the Maxwell laws and the wave equations. Thank you.